This is a short solution to problem 1.3.1, part 1 of Math 470, Real Analysis. This problem defines an unusual relationship. AB is equivalent to CD if A squared D equals C squared B. This is something relating to ordered pairs. We want to prove that this is an equivalence relation. To do that, we need to prove three things. One is that it's reflexive. In other words, A comma B is equivalent to A comma B. Secondly, we need to prove that it's symmetric, so that if AB is equivalent to CD, then CD is equivalent to AB. These we have to prove because it's not immediately obvious that they hold from the equation that defines the relation. Then we have to show that it's transitive. If AB is equivalent to CD and CD is equivalent to EF, then the first one, AB, is equivalent to EF, the last one. Why could this possibly be true? Let's think of it in a normal way. We cannot use this way for the proof, but we certainly can think of it this way to justify our thinking. A squared D equals C squared B is like the two fractions A squared over B and C squared over D to be equal. We can't use them as fractions, but if we think of the relationship that way, then it's pretty clear that it should be reflexive, it should be symmetric, and it should be transitive. Now all we have to do is to prove it. First, we're going to prove that it's reflexive. The way I'm going to remember the relationship A squared D equals C squared B is first squared times fourth equals third squared times second. To me, that's easier than remembering ADCB. So reflexive is AB equivalent to AB. Well, let's plug them in. The first is A, the second is B, the third is A again, and the fourth is B again. I'm just reading AB equivalent to AB from left to right and identifying the four terms as the first, second, third, and fourth. So it's first squared, that means A squared, times the fourth, which means times B. So if we put in the first, second, third, and fourth terms, we get A squared times B on the left-hand side of that relationship and A squared times B on the right-hand side of that relationship. Since obviously A squared times B equals A squared times B, we can conclude that AB is equivalent to AB, and this particular relationship is reflexive. Now let's show that it's symmetric. Symmetric means if AB is equivalent to CD, then CD should be equivalent to AB. Again, for me, it's easier to remember the equivalency rule as first squared times fourth equals third squared times second. So let's see if CD is equivalent to AB. We need to check that rule. In CD equivalent to AB, the first term is C, the second term is D, the third term is A, and the fourth term is B. When we stick all those in, we get C squared B with the first and fourth terms, and A squared D as the third and second terms. Is this equation true? Yes, it's the same equation as we started with. Because this equation is true, the relation is symmetric. Now let's do the transitive property. You might guess that this will take a little bit longer. We have three ordered pairs: AB, CD, and EF. Before we try to prove this, let's take a look to see if it has a chance of being true. There's not much sense in wasting time proving something that isn't true. So this relationship is kind of like A squared divided by B equals C squared divided by D. And since C squared divided by D equals E squared divided by F, this certainly looks like a relation that should be transitive. So we're trying to prove something that we believe is true. That's a good feeling. Now the proof cannot use division. We haven't gotten to division of these numbers yet. We need to start with what we're given, which is AB is equivalent to CD, and CD is equivalent to EF, and somehow get to the equation for AB equivalent to EF. Now let's see how that can be done. Here we have a table. The first two lines are what we're told are true. AB is equivalent to CD, and CD is equivalent to EF. I want to get that term to be A squared F. In the first line, it says A squared D, so I'm partly there. I'll multiply both sides of that equation by F. If we want to be really sticky about it, we would say that this is because multiplication is well defined. But we can multiply both sides by the same number. Now the left-hand side is in good shape. There is the A squared F. The right-hand side, it's still kind of a mess. We want to get E squared into there somehow. We're going to use that second equation. We have C squared BF on the right-hand side. C squared F is the same as E squared D. That's what the second line tells us. So between some associative, commutative, blah 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 properties, we can put the C squared F next to each other and replace that by E squared D. So if we look at that fourth line, the one that's marked associative commutative, we can see that we're almost there. We have exactly what we want, except there's that extra D on the left and the same extra D on the right. We can cancel the D. That's part 12 of Theorem 1.2.7. After we cancel the D, we get exactly the equation we need for AB to be equivalent to EF. That shows that this relation is transitive. So we showed reflexive, symmetric, and transitive. Therefore, it is an equivalence relation, and we're done.